So just quickly to recap from last week's lecture, we were using some of the chemistry of weathering to understand some of the long-term climate changes that we have in the Earth's climate. So over very long, tens to hundreds of millions of years, and that's due to the weathering of these silicate rocks via these equations here. So importantly, carbon dioxide, when it dissolves in water, breaks apart. Reacts with water to form carbonic acid. That breaks apart to form these dissolved inorganic carbon species, bicarbonate and carbonate, making the solution acidic. And then that acid can attack carbonate rocks and basically take that dissolved CO2 out of the atmosphere. It can attack silicate rocks, okay, and that takes 2 moles of CO2 out of the atmosphere for every 1 mole of silicate rocks. But the killer is that when all of those dissolved ions get into the ocean, they ultimately precipitate out calcium carbonate, so again, kind of shells, algae, sometimes produce calcium carbonate. And that precipitation reaction, dissolved calcium plus dissolved inorganic carbon, produces calcium carbonate, but releases carbon dioxide to the ocean. So this is a little bit counterintuitive because you're removing calcium carbonate from the ocean, okay? And calcium carbonate contains carbon, but that actually causes the concentration of carbon dioxide in the ocean and in the atmosphere to go up. So things like the formation of large coral reefs, that's actually bad for the climate in terms of it produces more CO2. So there's this idea that that removal flux from weathering of silicate rocks, because you get 2 moles removed of silicate rocks for every 1 mole, 2 moles of carbon dioxide removed for every 1 mole that's released then when it gets back into the ocean, is balanced by basically the global rate of volcanism. So when sea level is high, that means that it's probably high because of mid-ocean ridge spreading, kind of displacing the ocean. That increased rate of volcanism kind of adds more CO2 into the atmosphere. So this is kind of the idea. So when you start to grow a big mid-ocean ridge, like this one in the Atlantic, that displaces kind of the ocean. And that puts the ocean up on land. So not only are you adding CO2 in this case because you're increasing the rates of volcanism, okay, both at subduction zones and at mid-ocean ridges, but you're also flooding these continental shelves, making lots of shallow seas. That might promote the precipitation of calcium carbonate. That would then add more CO2 into the atmosphere. Okay, so there's an additional feedback process there to this adding CO2 into the atmosphere from volcanism. That causes sea levels to rise because of the building of the mountain range under the ocean. That raises sea level. That means that you get lots of shallow seas. You might precipitate more calcium carbonates as coral reefs or as shallow water carbonates. That adds CO2 to the atmosphere. So the other thing that's really important from the last lecture was this concept of feedbacks. So this is where you have some initial change, something makes the climate warmer, makes the climate colder, some initial change, and then there are processes within the climate system that act to either amplify that change, okay, that would be a positive feedback, or they act to moderate that change. So the classic example is snow cover. So if it gets a bit colder, gets a bit more snowy, okay, you might build some glaciers. Those glaciers are white, that reflects more radiation back out to space because of the higher albedo. That makes the planet cooler, that promotes more coldness, more snow, more ice, and then that kind of loop amplifies the initial change. Okay, an example of a negative feedback might be the weathering one, where you get a little bit warmer, that causes it to be warmer, to be wetter, then to be more biological cover on the land. That increases the rate of chemical weathering, which then removes CO2 from the atmosphere, reducing the initial warming. So feedbacks can be both positive and negative, and we'll talk a little bit about more of those today. So something you might want to think about in terms of the albedo feedback here is if we make it like very, very snowy in the winter. So large areas of the high latitudes are covered by snow. It's very white. Does that matter as much as if we were to grow an ice sheet there? So think about that, and I'll post that question in the discussion forum for you to have a think about. Okay, so today's lecture, we're going to be talking about slightly shorter timescales, moving on to this thing called glacial cycles, millennial scale variability. That's a blank page. What's that blank page? Oh, there we go. So, this equation is going to become really important. So we're going to try and use this to help us understand these changes. So the only things that we're thinking of changing are surface temperature, are the solar constant, so the amount of solar radiation we're receiving, the albedo, which is 1 minus the albedo, so higher albedo means colder, and the emissivity, so the greenhouse gas effect. So the first thing we're going to do is we're going to start looking at this period here where, this is a real cartoon of Earth's history, but where we're starting to get from a really warm Earth cooling down to the present over the last kind of 60 million years. So this is a kind of a less cartoonish representation of that. So this is 60 million years ago here, relatively warm, almost completely ice-free planet. And then over the last 60 million years, we've had this gradual cooling to where we are now in an icehouse world. We've got ice sheets on both northern and southern hemispheres. That's coming with this kind of sea level fall here. Okay, so this is a kind of a less cartoony version of that sea level fall that I showed you at that link. So one of the reasons that I've really suggested for this is volcanism. So we can look at rates of mid-ocean ridge spreading. So this is from magnetic stripes on the seafloor, and we can work out how fast they were spreading. We can kind of come up with basically a ratio of consumption of crust to production of crust, and that's with this graph here. So when we're positive on this graph, that means we've got lots of more mid-ocean ridge spreading, much more volcanism, so we should have much more CO2. So that kind of does explain some of this fall in temperature, because when we're down here, we should have more CO2 in the atmosphere, because we've got more volcanism. But there's other stuff going on as well. So at this time, so 60 million years ago, India was kind of like hanging out there in its ocean, the Indian Ocean. But then that gradually moved north and hit Asia, and that formed the Tibetan plateau up here, which is very high, very mountainous, lots of physical erosion going on there. So there will be a weathering response to that. Also, this mountain range is quite near the equator. There's the equator. So it's going to be in a region of high rainfall, so there's going to be lots of chemical weathering going on there. Anyway. So that will add to the drawing down of CO2, will add to the cooling. So we're going to talk now about a couple of things which are not in that equation, not in the equation for temperature, and that's the redistribution of heat around the planet. One of the ideas is that by reconfiguring where the continents are, so gradually kind of like drift around the planet, that can change the way that the ocean and also the atmosphere can circulate. So the idea is that at the moment, at the moment this is kind of Antarctica, and there's a gap here between Antarctica and South America, and there's a current that flows all the way around the continent. So this is called the Antarctic Circumpolar Current. It's one of the largest ocean currents. It is, in fact, the largest ocean current in the world. It's kind of like, it's approximately 20 times, I think, the strength of the Gulf Stream. So it's quite a big current. And this is important because if you look at this map over here, this is a map of heat flux. So this is basically heat coming into or out of the ocean into the atmosphere. And you can see that up in these high latitudes, you can see we have these big currents that are basically taking heat from down here and they're transporting it up into the northern latitudes. Okay? But in the southern hemisphere, we don't really have those. Okay? You can see one maybe starting to develop off the bottom of Africa here. Maybe one coming down the coast of Australia, but they basically get blocked by this current that's constantly flowing around Antarctica. So that means that Antarctica is isolated really from the rest of the climate system, so heat from the tropics finds it very hard to get down to this polar region here. So if we were to close off this gap here, I think, okay, all right, if we were to close off that gap there, then, do I have the next slide? No, I didn't. If we were to close off this gap here, then that would have the effect of stopping this current flowing around the Earth like that, and maybe water from up here would start to be able to flow down and around. Okay, so it would allow heat from the tropics to get to the poles. And that's important because if you look at the temperature gradients between the poles and the equator, so this is the present day, you can see that Antarctica is really isolated from the tropics. Not a lot of the heat from up here gets down to here. But if we look at a similar profile for basically mid-Cretaceous, which is a little bit before that 60 million years ago, but a similar profile would exist, is that heat from the tropics can get to the poles quite easily. Okay, because we have a slightly different configuration of ocean circulation. And that means that we're not adding any more heat to the planet, but we're evening it out a lot more, which means the poles are warmer, which means it's going to be very hard to have an ice sheet there. Okay, because ice sheets require it to be cold. And if you don't have ice sheets, then the planet would be darker, which would mean it will absorb more heat from the sun, have a lower albedo, and that will affect the global temperature. So a similar thing with the northern hemisphere is that there used to be a gateway here at the Isthmus of Panama. Okay, so the Pacific and the Atlantic used to be connected together here. That they're no longer connected. Okay, so when they were connected, warm water from the Atlantic could kind of flow into the Pacific, okay, rather than be forced up along the Gulf Stream. If you close this off, you kind of intensify the temperature of the Gulf Stream, and that's important because this Gulf Stream is responsible for taking heat and critically also moisture in the atmosphere. So if you make this bit of the ocean warmer, you get more warmth in Greenland, but you also get more rainfall. So actually making it warmer actually helps the ice sheet grow, because not only does it need to be cold, but it also needs to snow a lot to grow an ice sheet. So it turns out that for the Greenland ice sheets, this is Greenland without any ice on it. To get an ice sheet to grow on that, you've got to have some snow. Okay, so closing off this land bridge here means that warm water was able to get up here and cause there to be more snow, enable us to grow an ice sheet. So that is another thing that kind of cooled the planet. Okay, we can look at the close-up of the climate record now. So again, we've got oxygen isotopes telling us what temperature is, and as we come down towards the modern, these kind of closure of various seaways, this one is in Indonesia, Tibetan Plateau uplift. I think this is the closing of the Isthmus of Panama over here. But you can see these things add to this kind of cooling effect coming down to the modern. Okay, so I'm going to move on now to some of these shorter-term variabilities that we've just seen in that record there, at basically less than a million-year timescale. So this is the very last one of those cycles. So you saw in the figure before that the climate was bouncing up and down on its way down to the ice house world. And this is the last of those cycles. So this is now. This is the climate now. You can see that it was colder about 20,000 years ago. About the same as it was today, 130,000 years ago. So it's gone through, and these cycles continue on and on and on and on back in time. Okay. So the thing to point out here is that there are quite large amplitude changes. Okay, we're going to discuss how different those were. And there seems to be kind of a large-scale variation, and superimposed on that, a slightly smaller one. Okay. So some terminology that's kind of relevant for you guys here is that these things, because the temperature of the Earth is being recorded in oxygen isotopes, these wiggles up and down are quite often referred to as marine isotope stages. We're currently in marine isotope stage 1, and every wiggle you add one. So it's 1, 2, 3, 4, 5, and then it goes 5A, B, C, D, E, 6. The numbering is somewhat arbitrary in terms of whether it's a whole number or a letter number. So this first kind of really cold period is called the last glacial maximum, because it was the most recent maximum extent of glaciation. And when we have this transition from a glacial to an interglacial, that transition is sometimes called a glacial termination, because it's when the glacial ends. So this is kind of how different the planet was between these two states, between a glacial and an interglacial. So this is the northern hemisphere now, in terms of ice thickness. So you can see Greenland kind of there, having some ice thickness on it. Whereas if you look at 21,000 years ago, the ice was much more widespread in the northern hemisphere. So you can see Greenland's much bigger, also much thicker. There's almost 5 kilometers of ice thickness over Northern America, which is a huge amount of ice. There was ice over all of Scandinavia. Some of the Arctic Ocean was covered by ice, so it's not just sea ice. The ice was so thick that it actually bottoms out on the sea floor. You can see all of Iceland was covered in ice, a bit of kind of Scotland and Ireland was covered in ice as well. And also, because we've got this much more icy, much more reflective Earth, it was a lot colder. So these are kind of temperatures for the planet. You can see we're kind of in some places, because the temperature's not the same everywhere, maybe up to 6 degrees cooler in some places, which is quite a lot colder on average. So the question that one might have is that these changes, these wiggles up and down, up and down, up and down, up and down, do appear to be quite regular. Okay, that's a bit odd. So one might ask, what is causing those? So it's unlikely to be something kind of like volcanism, which is not really kind of would be thought to vary on a regular timescale. So there must be something regular that's driving these changes. And some of you might have heard of this actually glacial theory called Milankovich theory, which is the idea that changes in the Earth's orbit are responsible for the pacing of these glaciations. So this was a theory that was effectively first come up with this guy James Kroll, who's from Edinburgh. So of course I'm going to mention him. And he came up with the idea that the amount of radiation that any one latitude on Earth gets in winter is responsible for the timing of glaciations. And it turns out that they probably, I mean, this other guy Milankovich came along a little bit later and improved the maths of his predictions a little bit, but also came up with the changed the criteria. So it doesn't matter how cold it gets in winter, because it's the summer temperature that matters. So if you want to build an ice sheet, if you want to start a glacial, you can grow as much snow and ice as you want in winter, but if it all melts in the summer, you don't grow the ice sheet. Okay, so to increase the size of the ice sheet, you need to have cool summers. So that was the critical difference between these two guys' theories. But they were basically using the same set of criteria in terms of that the Earth's orbit around the Sun and the way that it kind of is oriented changes on a bunch of different timescales, and that doesn't really change the amount of solar radiation the whole Earth gets at all, but it does change how it's distributed around the Earth, and that's really important for determining the seasonality, so how kind of different winter and summer are. So the first one we're going to talk about is axial tilt. So this is basically how much the Earth's axis is tilted over. So this varies. Kind of the Earth's tilt sometimes is tilted over more, sometimes it's tilted over less. And this is really important because this determines how different winter and summer are. So if the Earth's axis was not tilted over relative to the sun at all, we wouldn't have seasons at all. Okay? If it's tilted over a lot, then winter will be a lot colder than summer. So we're in winter at the moment, we're kind of sitting up here. If imagine the sun is over here, we're pointed away from the Earth, from the sun. So that means that we have short days and it's cold. Whereas in the summer, the southern hemisphere is experiencing that at the moment. They're kind of tilted towards the Earth, towards the sun, sorry, and they're receiving longer days and warmer days because they're tilted towards the sun. So when summers are warm, okay, in the northern hemisphere, summers are also warm in the southern hemisphere. It's in phase between the two hemispheres. And it's got a period of approximately 41,000 years. So every 41,000 years, we go through a cycle of having kind of bigger amplitude seasons. So the next thing is this concept of precession. Now this is quite difficult to get your head around, but so the Earth orbits the Sun in an elliptical orbit, and if you can imagine, these red arrows now are the direction the northern hemisphere pole is pointing. So sometimes in the Earth's orbit we're quite near the Sun because we're following an elliptical orbit, and sometimes we're far away. But the direction which the Earth points in its rotation changes as you go around this orbit. So at the moment, when it's winter in the northern hemisphere, the Sun is pointed. The axis of rotation of the Earth in the northern hemisphere is pointed away from the Earth because it's winter. But at this time, we're actually closest to the Sun, whereas in summer we're further away. Okay. Now, where this point where we're pointing, okay, does change. So the Earth's axis kind of basically wobbles around as it kind of rotates around the Sun. On a time scale of 23 to 19,000 years. So in maybe in 10,000 years' time, we'll be completely out of phase in terms of when we're basically in winter now. So we're basically pointed away from the Sun. So this is winter now. This is winter in 10,000 years' time. We're pointed away from the Sun, but now we're much further away from the Sun. So that means that in 10,000 years' time, winter in the northern hemisphere will be a lot colder than it is now. Okay. Now, if you think about this in the southern hemisphere context, okay, southern hemisphere winter would occur here, okay, which means that the winter in the southern hemisphere would be warmer than it is now. So the phasing between the hemispheres is basically 180 degrees out of phase. So it also affects the magnitude of the seasons, but it does it out of phase between the hemispheres, whereas changing the tilt is in phase between the hemispheres. And then the last way that the orbit changes is that this ellipticness of the orbit of the Earth changes. So this is an actual representation of how elliptical the Earth's orbit actually is. Okay, so you can see it's actually quite close to circular. But how circular it is changes through time. So sometimes we're quite an elliptical orbit, sometimes we're quite circular. And this changes on quite a long time scale of almost 100,000 years, okay, between 95 and 130. And this has a number of effects, okay, but the biggest one is that it modulates the effect of the precession cycle. So imagine if you had a completely circular orbit, it wouldn't matter which way the axis of rotation of the Earth pointed. Whereas if you had a very elliptical orbit, precession matters a lot more. The other thing to think of is this kind of diagram that's whizzing around up here, in that if we have a very elliptical orbit, when we're close to the Sun, we'll have a lot more solar radiation than when we are away from the Sun. So there'll be a big difference between the seasons that way. But actually, when the Earth is close to the Sun, so imagine the Sun is here, we're close to the Sun, it swings past faster, and then it actually moves slower when it's further away. So this means that although this season here will be warmer, it will also be shorter. Whereas the season over here will be colder, but it will be longer. So these effects can kind of cancel each other out, or magnify them depending on what precession is doing at the time. So the overall effect of this, so if we look at the kind of the periodicities of these things, so precession varies quite high frequency, 19 to 20 kind of thousand years. Obliquity, which is the axis, the tilt, it's about 41,000 years. And then eccentricity varies on this kind of blue wiggle here with a much longer time period of around 100,000 years. Okay? If you add all of those forcings together, okay, you can get a curve like this yellow curve. Now, this curve will be different for every latitude on Earth. Okay? So you know that the forcing of obliquity will be completely out of phase between the north and the southern hemisphere. So it does matter where you choose what latitude your forcing curve is. But if you think the forcing at 65 degrees north is important, and people quite often choose that because that's where the big ice sheets in the northern hemisphere are. So if you're looking for the main difference between a glacial and an interglacial kind of climate, looking at where the position of the ice sheets changes the most, that's a good place to look for your forcing. Okay. So if we change the insulation in the summer at 65 degrees north, so that means we're having warmer summers, means it making it harder to grow an ice sheet. Okay, so that might kind of trigger a deglaciation. So when this is high, when these highs, okay, so if you look at the record of climate, it looks like these highs here do kind of coincide with these glacial terminations. Okay, now it does turn out to be a little bit more complicated than that, but you can see here how we can start to link these pacing of glaciation with the timing of these big changes. Okay. So the problem with this theory is that the actual forcing of these cycles. Oh, I was going to put a. Oh, there we go. The actual forcing of these changes. So the changes in S0 here are tiny. They're really quite small. Okay. So that S0 is 340 watts per square meters. Yeah. Whereas these changes are maybe in 1 or 2 watts per square meter, and they quite often cancel out over all of the globe. So when the forcing is high in the northern hemisphere, it's then low in the southern hemisphere sometimes. It doesn't completely cancel out, but it means that it's not enough. So it might explain when we get these glaciations, but it doesn't explain the magnitude of them. Okay, so you can see we have these huge changes in the climate. So 6 degrees Celsius maybe. We're looking at changes of building these huge ice sheets, which are I mean, if we were to rock up on a planet that was Earth, so we had a twin planet, it was the same, but it was in a glacial at the time, it would look completely alien to us. Okay, there would be So this isn't now in the glacier. This is just summer and winter. Okay, but so this is just the average snow cover. So you can imagine if these were the ice sheets, it would be completely unlivable North America. Most of Europe would also be pretty unpleasantly like Iceland in terms of barren kind of wasteland tundra type place. You wouldn't be able to grow trees, things like that, crops. To explain these really huge differences in the climate, we have to have some additional mechanism that's going to amplify these small forcings from changes in the orbit. And the most obvious one is this, okay, this albedo. So if you start to grow an ice sheet, okay, that can lead to this runaway albedo effect, where you basically have some cooling, you grow an ice sheet, the ice sheet reflects more radiation back into space because of the albedo, leads to a colder climate, and then it goes round and round and round. It gets colder and colder and colder and colder. Likewise, if you're deglaciating, you might melt a bit of your ice sheet, and then your ice sheet then gets smaller and smaller and smaller as it gets darker and darker and darker. Okay? So that's one possible feedback mechanism. Okay, so this is a close-up of that. You can kind of see, when there's lots of snow cover, the albedo of the planet definitely goes up. It gets a lot brighter. There you go. So much brighter, in fact, I had to change the colour of the equation so you can see it. Okay. So the other thing we can think about is the emissivity term in that equation. So the greenhouse gas effect. So this is you can't quite say that the red on here is carbon dioxide concentration. So you can see that that's changed in these days. Oh, sorry, I also flipped the years before present, so now time is going in a different direction. So this is old, and this is now. Paleoclimatologists do that quite a lot. It's very annoying. It turns out it's mostly because it's the way Excel plots data. So in physics and all other sciences, time moves from left to right. But because geologists deal with time in the past, we use numbers for that, and you put it in Excel, that will always plot smaller numbers on this side than that side. So this is a graph that's not been drawn in Excel. Anyway, so the blue curve on here is a record of temperature from Antarctica. Okay, so the numbers on here are effectively meaningless. They're not the real temperature, they're a proxy for it. But you can see here that the changes in temperature and the changes in CO2 seem to go hand in hand. When one goes up, the other goes down. Okay? So there might be, you might think, well, that's a forcing. CO2 is a greenhouse gas, so CO2 is causing all of these changes that go up and down. But there's no reason why CO2 on its own would change like this. So actually, in this case, CO2 is acting as a feedback. And there are lots of ways in which it can feedback, one of which is this solubility mechanism over here. So when something is cold, when water is cold, or you have horrible Scottish lager, it contains a lot of gas. Okay? Whereas if a liquid is warm, okay, so warm water or tasty English ale, there's less, you can get less gas in it. The gas is less soluble. And that's reflected on this graph down here. So as water temperature goes up, the amount of CO2 you can store in that water goes down. So that means if you warm up the oceans, because the oceans have got CO2 stored in them, if you warm up the oceans, you can't put as much CO2 in the ocean, so it must basically bubble out into the atmosphere. So that causes a positive feedback. So if you warm up the planet, the oceans get a bit warmer, CO2 will basically exsolve out of the oceans into the atmosphere, cause more warming, which will warm up the oceans, which will basically have this runaway feedback, and you increase atmospheric CO2, okay, as the climate warms. So there's a carbon cycle feedback there as well, okay? So you might also think, well, as you go up here, you might also kind of make the planet warmer, sea level is rising, you might flood the continental shelves a little bit, because you're melting all this ice. That might cause coral reefs to grow, because all this new space for them to grow. Precipitation of calcium carbonate releases CO2. So there's another feedback there that could add to the CO2 system. But effectively, CO2 has this solubility feedback. That's probably the most important one. There's also an albedo feedback that starts to magnify these small changes in orbital forcing, okay, which are determining the timing of glaciations, whereas the magnitude of the glaciations is mostly determined by these internal climate feedbacks. Okay, so we're going to move into an even shorter timescale now. So these are a couple of records from ice cores. So this is where we've basically drilled down into an ice sheet, two in Antarctica, places called Vostok Station and Dome C, and the two in Greenland. Okay, so these are the ones where you can basically count the layers in the snow and basically measure the bubbles in the ice and the maybe chemical composition of the ice itself to get proxies of temperature, things like that. So the thing you can see here is that we've got quite a lot of high amplitude, high frequency variation. Yeah, so you can see that the temperature, particularly in Greenland, is going up, down, up, down, up, down, up, down, up, down. Okay? And the important thing is that the time scale of that variation is quite short. So it's of the order of maybe a couple of 100 to 1,000 years. And this means that it's too short to be caused by orbital variability. Okay, because orbital variability, the shortest orbital variability was like 19,000 years. So if variation is happening on a shorter time scale, it cannot be caused by that slower change in forcing. It's also quite large amplitude. So if you look at Greenland, so this is now, so the difference between up here and down here is the whole glacial-interglacial cycle. And some of these variations here, maybe over half of the total change. So these are really big changes in climate. The other thing to notice is that if you look between the north, annoyingly the north is at the bottom here, so the north, and the southern hemisphere, they're not the same. So we're not talking about global climate changes now, we're talking about regional changes. Okay, we'll have a closer look at this relationship here. So we're just zooming in on those graphs a little bit more. So now I've put Antarctica on the bottom, Greenland is on the top. You can see that the changes do seem to happen broadly at the same time, but they're completely opposite. So when Greenland is cold, Antarctica is warm. Okay, when Greenland is warm, Antarctica kind of starts to cool down a bit. Yes, it's not completely out of phase, but it is definitely not in phase. Okay, and also the shape of these changes is different as well. So this is a lot sharper change with gradual changes in Antarctica. So this can't be caused by orbital forcing. It can't be caused by kind of long-term changes in CO2, because we would see that in the CO2 records. So one of the clues to what's happening comes from the marine record. So this is the North Atlantic, kind of where we're here. And these big splodges here and here are the location of some sediment cores. And there are more sediment cores over the whole North Atlantic. But one of the features of these sediment cores are that at these points when the climate in the Northern Hemisphere gets very, very cold, we have lots of this material found in the sediment core. So usually it's just kind of clay, mud, and some forams and kind of plankton that are forming these sediment cores. But when it gets very, very cold, we get a layer of this stuff. And this stuff is little bits of rock. And the way that this stuff is thought to get out here into the middle Atlantic is on icebergs. So icebergs, glaciers, they basically grind over the land. They basically pick up a lot of sediment, okay, that's very angular, that's basically just been physically weathered. And if you look at icebergs, quite a lot of them are not kind of like pristine, kind of shiny white things. They're quite dirty on the inside. I'll leave that there. So the idea is that something is causing these huge armadas of icebergs to basically to come out into the North Atlantic. We've got to think, what would the effect of that be on the global circulation? So let's just go through this cartoon here. So warm water, kind of, so the red on here is not only warm water, but it's the flow of surface water. So it goes round and round this gyre circulation in the Atlantic, and eventually gets into the Gulf Stream and moves north. And then when it gets into the north, so this is kind of up here, so this is a section to the Atlantic, north to south, kind of we're there. When it gets into this region here, it tends to sink down. Okay? It sinks down because up here the water evaporates, okay, which is why we've got such a wet climate, because the water goes into the atmosphere, which makes the water colder and it makes it more salty. And it's that salt that makes the water dense enough to sink to the bottom. That water sinking to the bottom basically makes a hole in the water up here that draws more water up into the northern latitudes. It doesn't actually create a physical hole, you can see, but water is drawn up by this sinking of water up here. And that effectively makes this limb of the basically North Atlantic drift up here transport heat from the Gulf Stream proper up into the high northern latitudes around Greenland. So this system kind of transporting heat is really important for keeping the northern hemisphere warm. If we were to turn that off, okay, if we were to suddenly stop the formation of that deep water, then this region would get a lot colder. What is that for? So this is the idea. What's causing these switcheroos in temperature? So if this flow of water is strong, okay, then we'll have it warm in the northern hemisphere. Okay, so we're transporting heat up there, and that heat's got to come from somewhere. It's coming from the southern hemisphere. So when it's warm up here, it'll be cold down here. And then if we can slow down this flow for some reason, then it'll be relatively more cold in the northern hemisphere, but so the heat will be trapped down in here in the southern hemisphere. So that explains this anti-phasing between these two records. So this is what might cause those switches. So we might have this normal, we have strong northwards flow, okay, that's transferring heat to the atmosphere, okay, it's making the water here salty so it can sink down to the bottom. Now, over time, if you do that, you're basically adding heat and extra snow to the ice sheet on Greenland, okay, and eventually over time that will cause there to be more runoff. So the snow doesn't just sit on the ice sheet kind of like moves out towards the edge of the continent where it's kind of warm enough to start melting. So if we increase this cycle here, we'll start to add more fresh water into the ocean around Greenland. Now, the effect of that will be to make this region of the ocean less salty, which means it'll be harder to sink down into the deep ocean, which means that this return flow will then be weaker. That means that then this region suddenly becomes a lot colder, okay, causing that switch in the two climate states. Okay? Eventually, because this region is now super cold, it's getting less basically snowfall, less heat, so there's less runoff, so this region of the ocean can gradually get more salty until it can suddenly start this overturning circulation, which will make it suddenly more warmer. Okay? So that's one way of potentially explaining it. That's not, the science isn't like done and dusted in this. It could be that there's another mechanism. So this is the continental shelf around Scotland, and you can see, if I up on there, you can see that there are basically a whole bunch of glacial moraines. So the ice sheets went all the way out to the edge over here, so kind of like this. So if you imagine that there could be some internal dynamics to the ice sheets that make them switch between a stable state where they're out on the edge, and they might then retreat back up to here, kind of like that. And that can either be thought of as a process like this, where you basically have heat melting from below. So if you put an ice sheet on the Earth, that pushes it down, and you push it down, and it'll be closer to the deeper, effectively, in the crust. The heat flow will be higher. And that might then cause melting, and then it melts, and then it jumps back to this stage here, adding kind of fresh water into the environment, which will affect the ocean circulation. Or, so it doesn't have to be heat from below, it could just be an ocean circulation, a sea level thing. So you start melting the ice sheets, and that causes this whole thing to lift off, okay, which will then cause it to break off and add loads of fresh water into the ocean. So there could be an internal ice sheet dynamics thing to it as well. So we've kind of touched on this, that there might be kind of two stable states, one where heat's flowing up to the north, one where it's being trapped in the south. So the climate doesn't, I mean, if you looked at that, the record of temperature in the northern hemisphere, it switched between the two quite sharply. So if we had a small change in climate forcing, let me get rid of that little thing. Okay, we don't have a gradual response. So if we change the climate forcing by a little bit, we make it cooler, reduce the forcing a bit more, make it a little bit cooler, and then if we change back, we go back to where we started. So it's not quite like that. It might be like a little bit more like this. So you might change the forcing a little bit, and that doesn't change the climate much. Then you get past a certain point, okay, and then a little bit of forcing flips the climate into a different state. Now, it might even be that the climate's actually more like this, where you could change the forcing backwards and forwards, and you change the climate a little bit, okay, until you get to this point here, and then suddenly we flip into this completely different climate state, and it doesn't matter how much you reduce the forcing, it's then very hard to get back into the initial state. So I'll just give an example of this kind of bistable climate state. Oh man, come on. Why is this not? Go away. I think I've broken it by not having it out. Anyway, so we're going to just have a really short period of climate change, so maybe 1,000 years in total. What the? Okay, so I have to use that anyway. So we're going to look at the Sahara. So at some point in the Sahara, so this is I think somewhere near in Mali, that's a carving of a hippo. It's not a very good carving of a hippo, but you know, it was thousands of years ago. That means that if people were seeing hippos at that time, so the Sahara now is very dry, not very hippo-friendly, means the climate must have been different. So we're going to have a look at this region called the Sahel, which is kind of this kind of region up here. Actually, it's kind of this box is in the wrong place. But this is quite a dry, arid environment. It's highly seasonal, so this is kind of after it's rained in the kind of the summer, rainy season, and then kind of the dry season. So it's very, very dry at the moment. It's not a terribly pleasant place to live. Not people get by. But if we look at the climate history of this region, so this is a sediment core that's been drilled just offshore here, basically 10,000 years old, young. You see it's time going the physics way, not the geology way. The radiative forcing in this region has been gradually declining. Okay, so that means we're getting slightly less radiation coming in, and it's thought that that's caused a gradual drying of the region. Okay, but if you look at the response, so what we're looking at here is, so again, this axis has been flipped upside down, annoyingly, but as we go this way, we're getting more terrigenous sediment, and that's because our sediment core is basically getting more dust. So you can see this is Africa, dust being blown from Africa offshore to here. So as the climate's gradually got drier and drier and drier, we've suddenly got to a point where it's flipped from being in this kind of lush green state, and that's because if this region of Africa is green, it's darker. It means it causes more basically internal cycling of precipitation and water. Whereas if it's slightly more arid, then that kind of retention of moisture within the local system breaks down, and the local climate switches into this kind of other stable state where it's dry, arid, and very inhospitable to hippos. So this is the idea of having a climate that can have two or more stable states, that it kind of jumps from one to the other, actually change the forcing gradually. And this is really important because it's thought that our climate in the future may behave in the same way. As we warm and warm and warm, if we then decide, oh, we'll just knock back the CO2, okay, by doing some geoengineering, it might not bring us back to where we started from. The climate might switch into a different state where it's permanently more warm. That was the end, but oh, come on. See how the recording deals with that. So to summarise, we've covered quite a lot today, so hopefully it'll all recorded. Let's hope for that. But basically the cooling over the last 50 million years, combination of reduced volcanism, so reduced mid-ocean ridge spreading rate, but also flooding of the continental shelves that might have, or basically the lack of flooding of the continental shelves might have stopped the carbonates being precipitated, which means we get kind of less CO2 in the environment, in the atmosphere. But also these things like changing ocean gateways, reorganising how heat is transported from the equator to the poles. That's an important part in global climate over long timescales. We have these orbital forcings which determine the timing of short 100,000 year climate changes, but the feedbacks are really important in determining the magnitude of those changes. So changing albedo, changing the greenhouse gas, so carbon dioxide. And then we have these millennial scale, shorter term climate changes, which are caused by basically the internal dynamics of the climate system. So flipping between these stable states, we maybe have small changes in forcing, or in some cases no forcing at all. Okay, so the climate might just switch between the two because of this, maybe this salt oscillator or ice sheet dynamics. Okay, that's it for the lecture, hopefully. So I'll see you all at the practical. So if you can all turn up to the Ashworth building, that would be smashing for 2 o'clock. And then we'll split into the groups. You should know what group you're in. You should have appeared on your learn groups. And then one group will go off and do some computing-based exercises, which will be fun. Okie dokie.